So today it'll be a mix of some odds and ends about pointed pseudo triangulations and some spinach, as Jordy calls it. So it'll be like a super lightning introduction to something that I'm not going to do justice to, but which unfortunately, well, fortunately, I have to introduce because it's very cool, namely Brisbane stability conditions. So I'll get to that in a minute. But first, let me just finish up like the cool stuff about pointed pseudo triangulation. So the thing that I kind of mentioned last time, but didn't say anything about, was the Carpenter's rule problem. Maybe I didn't say these words actually, but this is the problem which brought pointed pseudo triangulations into prominence. And the problem is very easy to state. I think it's maybe 40 or 50 years ago that someone formulated this problem. And the problem is the following. Okay, so here's, I'll just draw you some pictures about the problem. So suppose you have a polygon, a non-crossing polygon. Okay, so I have a bunch of points and I'm supposed to draw a polygon. So consider, and usually probably not convex. So suppose we have a non-crossing polygon. In R2, and once again thought of as a framework. So the question is, it's a framework, probably not rigid, so you can kind of move it around. Is there always a way to move it rigidly into a convex configuration, into a convex polygon? So question. Can you always convexify this via rigid motions? So it's a very, very simple question to state. And, I don't know who first posed it or anything, but quite a while ago, and it remained open for 25, 30 years or something. And then it was solved by three people, I think Connolly, Domain, and Rota. So the first solution around 2000 was and it was nice, but the second solution, which came right after, maybe even a few months after, or maybe even in the same conference or something, was the solution due to Strand, which involved pointed pseudo triangulations. Okay, so and the answer is yes. The answer is yes. Okay. So I will give a 2-minute sketch of what Strand's solution was. And the solution is literally an algorithm. So it tells you, look, if you have a polygon like this, here's what you do to convexify. And it's very elegant. It's really nice. I won't give you any details, but the idea is the following. And again, just through pictures. Okay. So the idea is this. The whole thing is not convex, probably, because otherwise there's nothing to do. So what you do is you take whatever edges you have and then fill in enough edges so that you have a pointed pseudo triangulation. So just throw in enough edges so that you have a PPT. So I'll attempt to do that. And these are kind of virtual edges. What do I do next? I guess I could do this. I didn't do a great job drawing this figure here, but maybe I'll do the other one. Okay, so now you have a PPT. Delete one of the outside edges. Don't delete an edge that's already in your framework. Delete one of the virtual outside edges. Okay, so delete this one. You have to have at least one of those because otherwise your figure was already convex. Okay, and now remember that a configuration like this has a unique expansive rigid motion. So expand. Okay, so step one, fill in to a PPT. Step two, remove a virtual external edge. Virtual meaning, not one of the ones that was already present. Step 3, expand, meaning move along the unique expansive motion. Okay. So what can happen as you do this? Either your polygon will become convex, in which case, great, you stop. Otherwise, you might run into an issue. And what issue might you run into? You might run into collinearities. Okay, so as you do this, you might imagine like you're expanding the polygon. It's like convexifying slowly, but suddenly 3 points become collinear, and then you don't know what to do. So you have to deal with that. So she found a way to deal with the collinearities, which I won't explain. It's very nice though. You either like if two of the edges of your polygon become collinear, you kind of just fuse the two edges, or if like one edge becomes collinear with a virtual edge, you perform some kind of flip so that you don't actually see that collinearity. So it's very nice. And then you deal with the collinearities, and in such a way that you can repeat this algorithm until you get a convex figure. So repeat and then profit. Okay, so this is the step which has the hard bit. But so this is the solution, and it's very nice. It's really, really nice. So this was Strand's solution, and she's the one who first proved all of these basic facts about PPTs in this paper. So it's also a nice paper to read. Okay, so that's all I want to say about the Carpenter's rule problem. This is kind of the history of the subject, maybe. It will probably make an appearance later in some form or another. We'll see. The second thing I want to say is the thing I didn't get to yesterday, which is, so we talked about rigid motions, and rigid motions give you one instance of PPTs because PPTs are minimally rigid. And if you take a PPT and you delete an external edge, you get 1 degree of freedom. So they're closely related to how to move frameworks rigidly. Here's another place where these things come up. Okay, so let me see how I want to. So maybe I'll also introduce some notation. Some of you may have seen this already, some of you may not. But we've been talking about. I've said a lot of things about points in R2, and we actually have some technology to deal with that. So what is this technology? It's called the configuration space. So what is this space? So there are several versions of the space. I can write something like conf n R2. People will might use slightly different notation. It'll probably ultimately be very close to each other, but notations can change. And so what's conf n? It's the space of configurations, the kinds of things that we've been looking at. So points in R2, such that PI is not PJ. Okay. So you can, this gadget allows you to take a configuration and move to another configuration, because this is now a topological space, evidently, and you can then think about paths in this topological space, etc. So it's good to have a tool to deal with this. So this is one thing. And the other thing, which is very closely related, is, so this configuration space is called the configuration space, the ordered configuration space of points, because I have an ordering on the points. And then I could think of an unordered version of this, so which is sometimes called uconf. So it's the same thing as before, but I'm supposed to forget the order, so I have to mod out by SN. Okay, so points in the plane, and distinct points in the plane up to reordering. Okay? And the points in conf don't collide, and so the SN action has no weird behavior. It's free. Okay. So this is just some notation, and then I'll introduce some other notation just to, because it's relevant anyway. So the other thing that I want to introduce is something closely related to these configuration spaces, which also ties into Jodi's lectures a little bit. But the point is, as I mentioned, configurations of points, if you think of a configuration as itself a point in the configuration space, then you can wiggle the points around without collisions and move to a different configuration. You could also take your original configuration, wiggle the points around without any collisions, and come back to where you started. And that would be a loop in configuration space. So we can think about like loops in configuration space. And why do we want to do this? Because we like to think about fundamental groups of spaces. Okay, so, oh, and sorry, one comment before I say anything. This is, I'm thinking about configuration space in R2. You could, of course, think about configuration space on any other space. But, okay, but this is like pretty important. So one thing which is also very important is the fundamental groups of these spaces. And I'll start with UConf. So the first proposition that I want to mention, and I'll mention the proposition, and then I'll say some words about what the fundamental group is, and maybe you've seen this before in some way or another. So if you take a configuration of points that's unordered, so one way to think about that is actually just to label the points, but then as I'm thinking about like moving them around, I can move them so that they come back to where they started up to reorder. Okay, so that's another way I could think about this. So I might have, yeah, sorry. So actually I'll draw a picture first. And this is kind of the standard picture that you may have seen. So I may have a bunch of points here. And then I want to perform some motions in the plane and then come back to where I started. And so the like traditional way that I've seen people draw this is kind of a vertical movie of what happens. And so you should think like, I have 3 points in this case, and I'm like moving them. So as I move them vertically, they'll form these string diagrams. So this gives you, you might have like this point might move around to here, but then the other points might like wind around this one. They may go behind and then come back in front, and then maybe come back behind. Hang on. And then this one might go down there, and then the third point might do something else. Okay? So each slice of this is telling me okay, so this movie is explaining how a particular loop in my configuration space looks like. And so all of this is up to homotopy, of course. Okay, so every horizontal slice gives me a configuration as long as I make sure that the strands don't collide. Okay, so this is what a loop in UConf looks like. And we've kind of seen these string diagrams before in Jodi's lectures when we looked at a presentation of SN. And so this kind of string diagram actually gives you a presentation of a different group, which is closely related to SN, which is called the Braid Group. Okay, so these kinds of string diagrams and all of what I'm saying can be converted into a proof. So this loop can be thought of as an element of the N-strand braid group. It's a loop in UConf. Did I make a mistake? Yeah. Okay, so this can be thought of as an element of the n-strand braid group. And what are elements of the n-strand braid group? In case you haven't seen this before, they're exactly string diagrams like this, which are more traditionally drawn as follows. So elements are string diagrams similar to the string diagrams of SN, except you have to remember which strand goes over and which strand goes under. So again, something like this. And then the products, I mean, multiplication in this group. Oh, and I should say, of course, string diagrams up to isotopy, continuous homotopy, okay? And then multiplication is stack string diagrams and pull tight. Okay, so if you take this string diagram and stack it on top of each other, top of itself, sorry, let's actually see what happens. Okay, so if I do this stacking and I connect strands, so I have like one twist on the left and one twist on the right. If this had been a string diagram in SN, the twists would have canceled themselves out, but here they don't. Here they just add. So I get two twists now. Okay, so this is a more complicated group than SN, but as you can see, it has a map down to SN because I can forget the over and under crossings. So this is the group generated as follows is called the Braid Group, BN. Okay, and in fact, one can prove that this, this movie that I drew, gives you exactly the fundamental group of UConf. So proposition, which I was about to write earlier, phi 1 of UConf is BN. Okay, so this is super nice. So this tells you something about the complexity of the space in terms of points moving things around. And now once we have this action, I can show you, not action, like the fact that the fundamental group is BN, I can show you what this has to do with pointed pseudo triangulations. Are there any questions before I do that? Yes. Yeah, that's a great question. So there is a little bit of choice. Like if I have 3 points in a configuration, how do I view them as a single line? Because it depends on my perspective. And that changing perspective is essentially like, it gives you the same group up to conjugation. So if you look at 3 points kind of with this perspective as opposed to from the other side, I'll basically take everything and kind of conjugate by some other some path that sends this perspective to that perspective. Basically, that was a good question. Yeah. But yeah, of course, you have to make this precise. Oh, and I'm sorry, I should say before I move on, since we've been thinking about SN, the standard presentation for BN is as follows. Again, if you haven't seen this before, just for completion. So you, just as in SN, you have points in a line and you have like, successive transpositions in SN. So this time you have successive twists in a particular direction. So maybe you can choose like whether you want to cross the left strand over to the right or the right strand over to the left. You make a choice, and then each such twist gives you a generator. Okay, so the presentation is one simple twist, I'll say, okay, for like between 1, 2, 2, 3, 3, 4, etc. And what are the relations? The twists no longer square to the identity, but they do still braid. So the square one relation goes away, and then you instead simply have sigma I, sigma j. Sigma I is sigma j, sigma I, sigma j. If I minus j equals 1, and otherwise they commute. So you can check this. You can actually check this using string diagrams. It's not too hard. It's nice to do. Okay, so this is just to complete the story, I guess. Okay, any other questions? So now we know about configurations. We know that it has fundamental group, which is the braid group. And so if I give you a configuration of unordered points, and if I, like do some extra stuff with it, probably the braid group is going to act on the extra stuff. So that's the heuristic. Okay, so let's do that. So what I'm going to do is the following. So let's look at, and I'm going to be a bit vague about conf and uconf. Hopefully it'll be clear from the context, but I deliberately will not dwell on that too much. So suppose you have a configuration. And suppose, so one thing you can do, and maybe it's not clear at the moment why I'm doing this, but I want to look at, given a configuration, I don't just want to look at a configuration, but I want to look at a configuration together with a single arc joining 2 points. Okay, so look at something like this together with, I could have, so configuration, so fixed configuration. And then within this fixed configuration, pick an arc joining 2 points. So I should be precise about what I mean by arc. So what kinds of arcs am I allowed? I'm allowed not necessarily straight line arcs, okay? So I'm allowed curves that begin at a point in the configuration, end at a point in the configuration, don't cross itself, okay? And also don't pass through any of the other points. So I'm like, I have to like wind around. So you should pretend that this configuration consists of pins, like in a notice board, and you're starting a string at a pin and you're like winding around the points and coming back somewhere, and you're not allowed to cross yourself. Okay, so let me write that. So arcs begin and end at points in the configuration. That are non-crossing, and 3 do not pass through any other point. Sorry, just a sec. Let me finish writing this. So don't pass through any point in the configuration except at the endpoints. Surprisingly long to write this. Okay. Yeah, sorry. Go ahead. You don't understand the proposition? It's so uconf n of R2 is a topological space. And I'm claiming in this proposition that the fundamental group of that topological space is the braid group. I don't think it's easy. It's not horrible, but I mean, essentially the proof, if you want to prove this, the proof goes through making precise these movie diagrams that I drew. So if you have a loop, I mean, an element of the fundamental group, oh, sorry, and I should have repeated the question. The question was, what is the proposition? What does the proposition actually mean? So if you have a loop in uconf, you can always realize the loop, in such a way. Then you have to say, okay, if I fix a base point in uconf, I draw a loop in UConf, I should be able to get an element of the braid group out of it. And I have to show the converse as well. So given an element of the braid group, does it actually also define a loop? And then you make this connection precise and you get the proposition. I mean, yeah, probably I think it is. Because the braid group is pretty complicated. So it's infinite, first of all. And yeah, I mean, the best I can do in terms of visualization, I think, is drawing movies like this, at least for myself. But I mean, one thing to note is that it does have, like, if you really just wanted to compute the fundamental group, there are simplicial complexes, which are kind of homotopy equivalent to UConf and things like that. So there are computational devices that let you compute these things. But if you want to visualize the space itself, I think it is complicated. Okay. All right. So, yeah, go ahead. Yes, the topology is inherited from R2. So you can, so these are, as you see, like conf is simply a subset of R2 to the n. Yeah, so, and then uconf is that thing mod Sn, and Sn is a discrete group. So you can give it the quotient topology. There are analogs. I think it's a huge subject, actually, like computing fundamental groups of configuration spaces. Yeah. Okay, very good. So let me draw a non-trivial arc. Sorry, 1 second. So a more non-trivial arc would be something like something that starts and kind of winds around and hits that. Okay, so okay, I introduced this whole braid group business for completion. Maybe you don't actually need the braid group to do this, but it's kind of there in the background. So the point is, if I start off with a simple arc like this, like, a straight line arc, I can now apply elements of the braid group to this gadget. Okay, so focus on this thing here. So it's just, a straight line arc between 2 points. I can take an element of the braid group thought of as the fundamental group of this configuration space. And what does that mean? Every element of the braid group specifies how to move the points around and come back to where you started. Now, as you do this, what are you supposed to do? You're supposed to take this arc and you're supposed to drag it along with you. Okay, so like, for example, if I take this point and if I move it up, then this arc will move up with the point. Okay, so again, they're like pins stuck to a drawing board. So you have to imagine like moving the pins around, and then the string kind of stretches and winds along with the pins. So you can imagine that there is an element of the braid group which takes the arc above to the arc below. That's not too hard to imagine. I think. Like there's it's complicated, of course, but so there's. Okay, so maybe I'll write that. So note that Bn acts on the set of such arcs. And of course, I didn't say this, but I hope that was clear. These arcs are arcs up to isotopy again. Up to continuous homotopy. So wiggling an arc a little bit doesn't change it, as long as I don't pass through any points. Okay, so Bn acts on the set of such arcs, and here's a proposition. Again, sorry, so maybe Bn wasn't really necessary in all of this, but it's important to keep in mind that you have it. So, okay, so before I state the proposition, actually, let's think about the second arc here. And once I have an arc, once again, thinking of the points as pins, I can now imagine the string to be a rubber band and just like shrink it. Okay, so that it'll hit some of the pins, that it'll go around, and it won't hit others, and so on. So if I do that, I'll get some like edges to which the arc snaps. And let me just draw in those edges. So visually here, you can see that it's going to snap to this edge. It's also going to snap to this edge. And then this part here is going to snap to this edge. And I'll snap here, and I'll snap here. So the configuration that I drew, I mean, the arc that I drew, sorry, if I snap it tight, you only see some number of edges. Okay. So also note that pulling an arc tight gives its, and usually I call it its support, which is some subcollection of the straight line edges. Right? So now you think about, like, you now like spend 5 minutes thinking about this, and you ask yourself, like, if I draw any arc of my choice, what kind of shape am I going to get? Like, what's the most number of edges that I can throw in given an arc? Obviously, they can't cross because that was part of the stipulation. So the edges that you get are going to be non-crossing. And 2 more minutes of thinking will convince you that every vertex has to have a reflex angle. Because if an arc is going around a vertex, then nothing else can intersect it from the other side. Okay, so that tells you the following proposition. Oh, and sorry, and there's thing number 3 as well, which is that the arc can't go around all of the points, because if it's not, it won't have any place to end if it starts somewhere. Okay, so here's a proposition. It's really an observation, but the support of any arc is a subset of a PPT minus an external edge. Okay, so the one that I drew here is not quite a PPT minus an external edge, but it's certainly a subset of such a thing. I mean, you can always complete it to a PPT minus an external edge. And in fact, the best you can do is a PPT minus an external edge. Okay, so there's an interesting question here, actually. So this is not hard. I mean, it's. I mean, if you don't see it right away, then think about it. But now here's the question, and I know an answer to this, I think, but it's not. I don't know an easy answer to this. Okay, so I pose it to you all as an exercise, and if you find an answer, let me know. So if I fix a PPT, fix your favorite PPT. PPT minus an outside edge. So can you always draw an arc which has exactly that support? Yeah, I mean, if you really force me, I can produce a proof of this, but it's not going to be a pretty proof. And if you find a nice proof, please let me know. So yeah. So I suspect the answer is yes. I mean, actually, I know the answer is yes, but it's an extremely elementary question to state, and I don't know the answer. Okay. Yes. Yeah, absolutely. I mean, you want to see like an actual PPT minus an external edge show up? Yeah. I'll show you in a second. So, yeah, the question was, can I actually draw an example with, how many points did I have here? 5. So I have to I have to rack my brains a bit, but let's see. Maybe actually, you know what? I'll do it with 4 points first, just as a warm up, and then not sure if I can do it with 5 points in real time. I think I can. It's easier with the convex configuration. Okay, so with 4 points, here's one. 4 points I've drawn a lot. And here's another. So this one gives you this diamond. That's a PPT minus an external edge. This gives you a triangle with a dangling arm. Also a PPT minus an external edge. And with, I'll draw one example with 5 vertices, but to make my life easier, I'll draw a convex one. Does it? I mean, I'll have to extend it because it doesn't have enough edges. Oh, yeah, actually, maybe you're right. So maybe, no, you're right. You're right. Okay, let's do that. Okay, so you're saying, I think if I understood you correctly, instead of just stopping at this point, I could keep going. Wow, didn't mean to do that. Keep going. And in there. And now I pick up this edge. Yeah, very good. So, and then here I can do something like, there are many ways to do this, of course. For convex points, by the way, I do have a nice answer. I mean, that's the first exercise. So here, once again, here's a triangulation. Almost, I've just deleted an outside edge. So you can, yeah, it's kind of fascinating. Yeah, you can do lots of things. Any other questions or comments? Yeah. Yeah, I mean, it's the hardness is, oh, yes, thank you. The question was, is it easy to see why the braid group action that I mentioned is well defined? And the answer is essentially, yes, if you like stare at the proposition long enough about the pi1 of uconf being Bn. So as you like, if you like really explore that proposition, you even explicitly find generators for the braid group action and things like that. And then those generators are local topological operations, which are like you're doing something up to isotopy, and then you can kind of patch them together to make sure that the action is well defined on all curves. Yeah. Yeah, maybe it's not like obvious on the nose, but more or less. Other questions? Okay, so we are done with temporarily with this part of the story. And now we come to the third thing from today's lecture, which is the spinach, which we don't have a ton of time for, but you know, I'll see what I can do and continue next time. So 3. So I had explained, I think, on the first day that at some point the difficulty is going to ramp up, and this is that point. So if you haven't ever seen these words before, it's totally fine. If you've never seen a triangulated category before, totally fine. I'm going to try to give you an intuition without giving any explicit definitions, because the definitions typically take 3 hours to give, like if I really want. So we don't have that much time, unfortunately. So I will, yeah, I'll try to say some words. They are not going to do it justice, but hopefully will give you something. And then if you have seen the definitions before, hopefully you can get more out of it. So what I'm going to work with eventually is triangulated categories. Okay. So we will look at and as I said, I don't plan to give the definition, but I'll give you like 2 or 3 kind of like toe holes maybe, okay? So we already saw this morning this category like DBC of something in Jodi's talk. So if you have these kinds of derived categories are prototypical examples of triangulated categories. So if you you are welcome to think about derived categories, bounded if you like. And the salient, like 2 or 3 salient features about these categories, they're big, okay? They're not usually like, they don't usually behave like abelian categories. They have certain operations on them, which I will write down. And you can take these as black boxes if you haven't seen this before, okay? So there's a shift operation, which typically people write as shift by 1. So meaning if you have an object in such a category, you can always shift it. I think of shifts left and right, but it's up to you. So for every object, there are objects x shifted by n. Okay. Positive and negative shifts. And then the second thing I want to say, which may show up, and that this is the last thing I want to say about triangulated categories at the moment, is that the basic building blocks are what are called distinguished triangles. And these are like the basic gadgets that tell you the structure of this category. So they tell you what things map to what and what are the properties of these maps. Okay, so people typically draw them like this. And I'm just simply going to leave it at this. Okay, so distinguished triangles look like this, whatever the heck that means. But it's telling you some basic relationships between objects in these categories. Okay, and if you're coming from an abelian category perspective, people often like to say, oh, triangulated categories don't have exact sequences, but distinguished triangles behave like exact sequences. Now, when I first heard that, that meant nothing to me. So I'm sorry if that's you, but I will repeat it anyway. Okay, so that's all I want to say. But the basic example to keep in mind is derived categories. But now I want to think about triangulated categories without actually thinking about triangulated categories, just to make my life easier. Okay, so the next thing I want to talk about is I mentioned the triangulated categories are often quite big. You know, the tools that you use to like think about objects in them are often different from what you think about in abelian categories, but sometimes you're in luck. Sometimes triangulated categories have something called a bounded T structure on them. Okay, so if you're lucky, you have what are called bounded T structures. On your triangulated category. And I want to focus on this, and I'll say a little bit about what this is. And the reason why I like bounded T structures in this context is that, you know, triangulated categories can be like quite a mouthful to study, but if you have a bounded T structure, what you have, so on your triangulated category C, okay, so what is a bounded T structure? This is some full abelian subcategory which essentially captures all of C. Okay, so abelian subcategories are a bit easier. Again, if you haven't seen abelian subcategories before, think of, you know, like the easiest example would be like vector spaces or something, but think better would be to think of representations of your favorite algebra. So what can you do with representations? You can take direct sums of representations, you can have maps between representations, you can take kernels of representations and maps, I mean, and co-kernels and things like that. And those are the kinds of things that abelian categories have in them. And they're somehow more familiar if you first learn about the subject. So if you're lucky, you have bounded T structures on your triangulated category, and a bounded T structure is a full abelian subcategory A inside of C, which captures all of C up to shift. Okay. And this is, I've made this precise in the notes, so you're welcome to read that or come and talk to me. But roughly speaking, what this means is that if you have any object in C, that object may not live inside A, of course, because A is like just a small part of C, but every object will have a filtration such that every piece lives in some shift of A. Okay, so this means your study of objects in C basically kind of reduces to studying objects in abelian categories, because you can just say, okay, fine, I don't have something in an abelian category, but let me just like break it up into pieces where each piece lives in an abelian category, and that makes my life easier. So that's the idea. And then if you have something like this, then you basically reduce. So this lets you essentially reduce calculations in C to calculations in A. Okay, so that's what the idea of a bounded T structure is, which is great. And then I have 3 minutes, so I'll get us started and then complete next time. So okay. The whole beauty of triangulated categories, especially if you have bounded T structures, is that, you know, okay, fine, you found some full abelian subcategory that captures C up to shift. That may not be the only one. Like, you can have other T structures on C. So like maybe you study your category C with respect to some T structure A, or like abelian subcategory A, but there's some other abelian subcategory sitting inside, which gives you like a different decomposition of C. So this is the whole beauty of the subject, because you're not limited to A, but it is nice to have A. If you have one, you can at least use it, but you don't have to use the same one. You can use, like, there's lots of combinatorics of changing T structures around. And one kind of aspect of that is given by Brisbane stability conditions. So I guess I really don't have time to talk about that today. So unfortunately, I'll have to defer it to tomorrow. So let me see if I can make any other illuminating remarks. So remark number 1 is it's very useful, so rich and useful to vary bounded T structures if they exist. And you can get a lot of like really nice combinatorics out of varying your bounded T structures. There are procedures to, like, given a bounded T structure, changing it to something else. And the other couple of remarks that I want to make about terminology, which just so that we are all on the same page, is that if you have a bounded T structure which, does this, then this A here is called the heart of the T structure. So you can simultaneously have lots of different bounded T structures, lots of different hearts, which kind of like fit together to give you all of C. If you have access to one of them, you basically understand all of C, but then having access to more than one is even better. And so one of the exercises today is a construction of a non-standard bounded T structure on kind of a standard derived category. Some of you have seen this exercise before, I think. But yeah, that it's really instructive to do. I really recommend you do it if you've never like kind of played with these structures before. And then tomorrow, I think I will discuss something about bridge stability conditions. It'll be some more spinach, but then we'll come back to pictures again. Okay, thanks a lot. Yes. Does the Braid Group act transitively on the arcs that we are interested in? Yes. That's not too hard to show, actually. That is an excellent question. The question was, is there a description of the snapping process in terms of the Braid Group elements? Yes, that's actually part of like what I'm working on right now. So I'm happy to give you more details in office hour. Yeah. Very cool. Yes, very good. So the question was, what makes the T structure bounded? The answer is embedded in the capturing, which I didn't say much about. So I will elaborate on that in just a minute. To shift, sorry. So I said this in words kind of quickly. If you have every object, if you have any object in C, then it has a filtration such that every like piece of the filtration is an element of A up to shift. The boundedness comes in the fact that this filtration is finite. So if you have the nice thing about bounded T structures is that you can have unbounded T structures, meaning you can have something similar where like every object is captured up to a not necessarily finite filtration. But then your study of C doesn't necessarily kind of reduce to the study of A. You have to maybe do something more complicated. But in a bounded T structure, you're really fine. You can really just study A and then study every object and look at its filtration and then start, get a handle on that object. Any questions from Hawaii? Okay, let's stop there then. Thanks.